How's everybody doing? Doing okay? Second week Wednesday. Things are starting to pick up a tiny bit, maybe. Okay, so I think what I'm gonna do, because a lot of these times I find myself still working on whatever notebook it is that I want to present in class. So I've created a little GitHub repo for our class, and I'll just post our notebooks, and then that way you can go to the repository, and then the numbering system will be the week followed by the lecture. So 0201 will be second week Monday, and then we'll have 0202 for second week Wednesday, which is today, and so on and so forth. That's kind of the plan here. And then and if there's questions in class that come up, I'll probably add to the notebook and make changes. So on Monday, I think Priyanka, did you ask about the shallow copy versus the deep copy? Okay, so I looked that up, and I don't know if anybody checked this out, but just very quickly, this is the difference between shallow copy and deep copy. So if you do list.copy, or you do the list and then the square bracket and then the empty slice, which does a shallow copy, then you'll get we'll discuss the shallow copy, whereas you can create a deep copy, but in order to do that, you have to use the command copy.deepCopy. First, you have to import kind of the copy module or library or function here, okay? And so here, I've created a list A and a list B, and C will be another list that consists of object A and object B, and I'm going to not even copy, I'm going to just say D is equal to C. So here we're not making a copy. Both D and C refer to the exact same object. So when I print out C, I get a list of lists where the first list is A12 and the second list is B34. And then when I print out D, I get the exact same thing. And then if I modify list C by saying item at index 1 is going to become the string X, then that modifies C and it modifies D. So when I print C, I get A12, it's still the list at A, but then the second object in the list gets replaced with the string X. And that affects both C and D. Okay, is that all right? Do I need to zoom in? Maybe I'll zoom in. There we go. Whereas if I do copy, then we have the copy going on, okay? So here is A, B, and C. Again, A is A12, B is B34. C is the list consisting of objects A and B. We make a copy, okay? And here I'm going to assign the item at index 1 to X in C. So this changes C, and I get A12X, but then when I print out D, I get A12B34 because D is a copy of C, so the changes made to C do not affect D. Okay. However, because it's a shallow copy, when I look at item A still refers to the original list A. So I can modify list A by appending the value 100 to it. Okay. And then when I print C, which is defined by list A and, now is X, becomes A12-100X, and then D is also affected because we've modified A and D points to object A. So I get A12-100, and then B is unchanged, B34. Okay. All right, over here I'm going to have ABC again. This time E is going to be a deep copy of C. A deep copy of C copies list C and also creates copies of the objects inside that are referenced inside that list. So here we've got, if we change X here, just like before, it changes the item at index 1 to X, and E is unaffected by that change. Now I can append 100 to list A, and when I print out C, it gives me A12-100 and X. However, when I print out E, because it was a deep copy, it created this thing is not affected by appending 100 because 100 affects only list A, and within list E is a copy of list A, not list A itself. Is the distinction there clear? So when you create a shallow copy, it creates, you're referencing the items that the original list referenced, whereas when you create a deep copy, you are creating copies of objects that are nested inside the list. Okay. So anyway, and then I updated the string section with a few more string methods, and I encourage you guys to read through that. But I don't want to dwell too much time on stuff that we've already covered. Okay. And so anyway, I think this is what I'm going to do. Rather than posting notebooks here, I'll just, here's the link to my GitHub repo, and then you can go to the repository and see the latest version, most up-to-date version of whatever notebook it is I've created. Is that okay? All right, so today I want to cover NumPy. Okay, so on Monday we covered just some basic stuff in Python. We looked at lists and we looked at strings, and we didn't really look at other data types like integers or floats, but those are fairly basic. What we're going to look at here is the NumPy array. Okay, so with a regular Python list, you can have different data types. You can mix strings and integers and all sorts of stuff. With a NumPy array, all the values inside the array have to be the same data type. Okay, and by making this change, by requiring everything in the NumPy array to be the same data type, we gain a lot of efficiency in terms of calculations. So when we want to do kind of some linear algebra and do like matrix calculations and things like that, NumPy arrays will be how we need to do it. Okay. Here, sorry. Let me. Okay, and so I guess if you're coming from R, the NumPy array can be thought of as similar to a atomic vector or matrix in R, because in atomic vectors in R, everything has to be the same data type. Okay, except in Python, this ability to create a NumPy array is not in the base Python, and so you have to import the NumPy package in order to do this. And the way we do it is we always write import NumPy as NP. Okay, this is an important thing. If you don't write it like this, people are going to have a hard time understanding your code. This is kind of like a universal convention. Okay. In the way that nodding your head means yes and shaking your head means no, it's kind of an arbitrary choice, but everybody understands that that's what it means. And so if you decide one day that nodding your head is going to mean no, people are going to be confused. So follow the convention here, right? Okay. So the way we create NumPy arrays is you take a list and you throw it inside the function np.array. Okay. So you do np.array, and then here I've taken the list 1, 2, 3. So we've got integers 1, 2, 3, and now it says, okay, this is now an array. All right, and if you just do this in IPython, it tells you array parentheses and then bracket 1, 2, 3. Whereas if you print out that thing, you get something that looks like this. And the way we kind of differentiate between an array and a list is that the list will have commas, whereas the array will not. Okay, if your list mixes data types, okay, such as 1, 2, and 3.0, then everything gets coerced, or Python calls it upcasting. Okay, so the 3.0 is a float and will upcast. In R we call this coercion. Upcasts the other values to floats. Okay, and so you can tell that they're floats because now they have little decimal places to indicate that they are floats. Okay, same thing with strings. This will upcast to strings. Okay, and so if one of your things is a string, then everything gets turned into string objects. You can provide it a list of lists. So here I've got a list, and inside that list I have two lists of length 3. And so if I do that, then NumPy understands that this is like a matrix, and it kind of stacks them on top. Okay, so here I've got a list with lists inside, and when we do that, it looks like this. This is basically the equivalent of a matrix. But if the list that you give it, the dimensions don't match, then you'll get an array of lists, which is not as useful for us. Okay, it doesn't try to do doesn't fill in values or anything like that. Okay, so this is kind of your basic way of creating an array by feeding it into np.array. Over here, we have other functions to make arrays. So if you just need to make an array quickly, you don't have to make a list first and then feed it in. You can use functions like np.zeros. Okay, so all of these NumPy functions start with, because we've imported NumPy as np, all of our NumPy functions will start with np dot something to indicate to Python that we are using the function within the NumPy package here, or NumPy library. So I've got np dot zeros, and 5 says make basically a vector or an array. Sorry, I'm using the wrong terminology. Make an array of zeros. So in R, that would be similar to saying repeat 0 5 times. So it says make an array of zeros. And the default number type when you use zeros and ones is going to be floats, float 64s. You can specify and say, I want integers by doing np.zeros 5 dtype equals, do I write int? Yeah, okay. So you can say dtype equals int, and then it'll make them integers. But the default is floats, and that's probably fine. Okay. If instead of giving it just a single number, but you give it a list or tuple of multiple dimensions, okay, so here it will create an array that's 2 by 4. So np0 2, 4 will create a 2 by 4 array, right? And you can, so this will be two rows, 4 columns, and you can give it multiple dimensions. So you can create a 3-dimensional array by doing 2, 3, 4, and notice the order in which these kind of dimensions are created. First, we're getting 2 sheets, and each sheet has 3 rows and 4 columns. Okay, and I think I can even go like np.zeros. Let's do 2, 3, 4, 5, and this will be huge. Okay, so this is like the first, what do I call this, prism? It's a little bit hard to see, but the way it differentiates is it kind of puts a larger space, and we got all these more brackets here. So this is like the first block. The first block has 3 sheets, Each sheet has 4 rows and 5 columns. And then the second block also has 3 sheets. Each sheet has 4 rows and 5 columns. So you've got, this is a 4-dimensional hyperprism, hypercube, consisting of, you know, two 3-dimensional things.
Wait, yeah. What's the 3 in this one?
The sheets. So I don't know. So it would be blocks, sheets, rows, columns, if that makes sense. Okay. Whereas if you're coming from R, the specification was rows, columns, sheets, blocks, hypercubes, hypercubes, whatever, you know, as the arrays get, you know, even more and more multi-dimensional. Yeah, I don't know if I want to keep that, but okay. So that's np.zeros. If you instead want ones instead of zeros, you have np.ones, okay? And then if you want a value other than 0 or 1, you can do np.full, and you specify the dimensions and you specify the value to fill, okay? But np.full, it only just takes one value, whatever that value is, and it throws it in everywhere. Is that okay? Okay, sometimes you want to make random numbers, okay? Random numbers, all of the random numbers will start with np.random. This tells Python that we are using the kind of the random module within NumPy, okay? If and just because these are pseudo-random, you can always set the seed for reproducibility. So you can do np.random seed, okay? And then random.random is going to be kind of your random uniform from 0 to 1, okay? So random.random is your standard random uniform. And here, this will give us back 5 values from random uniform. And then random.random rand_n, this is for random normal. This will generate values from the standard normal. So random.rand_n5 will give me 5 values from the random normal. If you want to specify things other than things from the standard normal, then you can do np.random.normal, and you would specify the mean, the standard deviation, and the kind of how you want to arrange it. So here you can just give it like 5, and it will put it, you know, a one-dimensional thing of length 5. Or here you can say 2 by 4, and it will give you a 2 by 4 array or matrix, however you want to call it. Or you can use rand_int, and this will sample values of random integers between 0 and 0 inclusive, but 10 exclusive. So basically 0 through 9. And 20 will say, I want 20 of these values. So here this will be random digits from 0 to 9, 20 of them. Okay, and then there's a ton of other random routines, and you can always read up on the documentation. So if you want from the beta distribution, binomial, chi-square, Dirichlet, exponential, gamma, all of those, so many random distributions, okay? And you can get values from any of those things depending on your needs, okay? And then if you want permutations, you can do shuffle and things like that. So that's random numbers. Other things are you want to make sequences, okay? So, you know, in R it was really easy. You would just do like 0:5 and you'd get the numbers 0 through 5, okay? With NumPy, it's not one character, it's not the colon. You've got to now specify a few things. So you have a range, okay? So there's actually a command called range within regular Python. Oops. Here, let me. So you have the range command like this. Yeah, I guess it just prints it out like this. Okay. But and this creates a range object in Python, and in regular vanilla Python. Okay, but in NumPy, the A range is very similar to the range thing, except the result of it is going to be an array. Okay, so that's what the A stands for. It's array a range. Okay, makes a range in the array, and it says, and the parameters are where you want it to start, where you want it to stop, exclusive, and the step size. So if you do 0, 100, 5, you're going to start at 0, go up to, but don't include 100 by 5. So it goes, 5, 10, 15, all the way up to 95. So it's kind of like sequence in R. In R, you have the sequence thing, and then and another thing that makes a sequence. But in R, you used kind of length out or out length or whatever it was. Here it is you have Linspace, linear spacing. Okay, so it spaces out the things in a linear manner with a start and a stop and how many values you want. Okay. Why did this double start? Okay. So linear spaced values. So starting at 0, ending at 100, and we want a total length of 11. So that will go 0, 10, all the way up to 100. So that will have an output length of 100. So with Linspace, the stop is included by default. If you do Linspace 0, 10, 0, 100, comma 10, the output length is going to be 10, and so this might not be exactly what you originally anticipated, but this is what you need to go from 0 to 100 by step size of 10. You're basically incrementing by 1/9, or 100 over 9. Okay. If you include the optional argument endpoint equals false, then you can go 0, 110, and it will go by tens, but it'll end at 90. So it doesn't include the 100 there. All right. So this is kind of making sequences for your arrays. Is this all okay? This is all like vocabulary, all right? And so, in the beginning, when you're learning Python, make yourself some flashcards or whatever, and just kind of practice using your vocab terms. Okay, it's just like learning a foreign language. Okay, except it's a foreign computer language, and you've got to. The only way you're going to remember these terms is by using them or kind of practicing them. So, we'll have a quiz on Monday again, and it'll basically be a vocabulary quiz. I'll probably have like some input and then some output, and I'll ask like, what was the command that went between the input and the output to? So it'll be like, the question will look maybe something like this, right? Here's the output. What was the command that went in? np dot, and you would need to tell me that the command was a range 0, 100, 5. Okay, you can look at the attributes of an array. So you've got dimension, shape, number of dimensions. So actually, ndim is number of dimensions. Shape is the size of each dimension, and dtype is the data type. So here I'm creating this array of ones, 3 by 4. Okay, so if I ask what are how many dimensions there are, it'll say this is a 2-dimensional NumPy array. The shape is it's 3 by 4, 3 rows, 4 columns, and then the data type contained in this array is float 64s. Okay. If you do something like np.arange you are going to get a one-dimensional array, okay? And you ask for the shape. Here, I guess I can insert a few things. So if I do y.ndim, what will this return? It'll return, oh, I haven't defined y. Okay. I was like, what? Okay, so here I've defined y as np.arange, okay? And if I ask, how many dimensions does y have, it'll tell me it has one dimension. And so if you ask for the shape, it tells you 12 comma, indicating that there's just one dimension. It's not 12 by 1, there's only one dimension 12, okay? So there's only one dimension with a length of 12 here, okay? So that's what we have. So that's important to note. This is not it's not a 1 by 12 matrix. It is just a array, a one-dimensional array with a length of 12. Okay, it's different, right? Just like in R, you had atomic vectors that were one-dimensional, and if you asked for the dimensions on a regular vector, you would get an error there. Okay, whereas you could have a 1 by 12 matrix, and it looks similar, but that actually has two dimensions. So similarly, this is one-dimensional, and if it's one-dimensional, there's only one dimension there. Okay. We can reshape our arrays, okay? And the command for that is np.reshape, okay? So here I would say reshape, and then we give it the array, and then we give it a list with the new shape. So here J is going to be an array range, okay? A range of 0 to 12 by 1, so we got 12 values in J. And then if I want to turn this into basically a matrix of 3 rows and 4 columns, I would do np.reshape, reshape the array J so that it has that it's 3 by 4, 3 rows, 4 columns. And when we do that, K comes out, and indeed we have 3 rows, 4 columns. One thing to note if you're coming from R is that it fills in the values row-wise, okay? In R, we filled things out column-wise. Here, it fills them out row-wise. If you want the transpose, you would just do k.t, k.capital T. This is the transpose of k. Okay, so this is not. So the notation is a little bit different, right? Here we're calling the reshape function from np, so we're doing np.reshape. And here, if we just want to transpose it, we take the array and we say array.t, so it's k.t, and that gives us the transpose. Okay, and some methods actually affect the original object, just like when we called if we had a list A and we said list A.pop, it actually modified that thing, or A.extend or A.append. It actually modifies those things. K.t does not modify K itself. So if I go back and I say print K, it's in original form. Okay, this was like several steps to go from J, the A range, to reshape it to the transpose. Okay, a nice thing about Python is you can just kind of tack on these commands one right after the other using kind of the series of dots. So you can do np.arange.reshape.t. Okay, and it's almost like pipes, but they're not pipes. It's basically this creates an object with which has methods, and you're just using the methods within the methods. Okay, so you say starting in NumPy, create an A range, then you reshape that so it has dimensions 3, 4, and then you're going to take the transpose of that, and now we have something that looks like this. Okay, so we don't have to go step. J is the A range, K is the reshape, and L is the transpose. You can just go directly A range reshape T. Is that all right? Okay. Just to reiterate that if you have a one-dimensional thing, okay, So here is a range 0, 12, 1. Okay, this is a one-dimensional array, a vector per se. The shape has only one dimension, okay? And it's got basically a length of 12. And if I say, give me the transpose of that, it doesn't turn it into a matrix and make a column out of that, okay? It's still just a one-dimensional array. And if I ask, what's the shape of y.t.shape, it's still exactly the same of 12. Right? So if you wanted to turn something into from a one-dimensional thing into a column matrix, okay, then you have to reshape that so that it is one row, 12 columns. Okay, so now it's a matrix with one row and 12 columns, and the shape says one row, 12 columns, and you can transpose that, z.t, and that will be 12 rows, 1 column, and if you ask for the shape there, it's 12 rows, 1 column. Okay, so again, if you're coming from R, in R you were allowed to just kind of take a vector and say transpose, and then it would kind of coerce it into a matrix and try to transpose it. NumPy doesn't do that. Okay. Okay. We need to subset and slice arrays and things like that. This is a lot like subsetting and slicing a list. So here we've got a one-dimensional array. You can say, give me the item at index 4, and it does. And you can say slice from 4 to 6, okay, and that will go give you back 4 and 5. You can also give it a second colon when you are slicing, okay, and when you do that, it will be the start to the stop and the step, okay. So this will say start from 1, stop at 8, and only give me back the third item. So we're going to start here at 1, and then we go 1, 2, 3, and it gives me back 4, and then 1, 2, 3, and it gives you back 7. So that's what we have here. Did you have a question?
No.
No. Okay. Okay, and then to subset, if you've got two-dimensional objects like a matrix, okay, so here I'm going to just reshape Z so that it's two-dimensional, so it's 3 by 4. We've got this, and if we want to return, you can subset using kind of the square brackets with a comma, and this will say what is in row index 1 and column index 2. So row index 1 is basically the second row, and column index 2 is the third column, and that will give you back the 6. Okay, and when you ask what is the type of value here, this value 6 is not an NumPy array. It is just an integer. Okay. Whereas if you can also specify slices. Okay. So here we can subset Z and we say, give me back rows from 0 to 2 and columns from 0 to 2, and so that will give you basically this 2 by 2 corner up here, and so we get the array there. And then if we ask what is this type, this is a NumPy array. Okay, and similarly, if you want the entire row or the entire column, you do Z2 comma, and then you give it empty slicing. Okay, and this will give the entire row, and then and this will be a one-dimensional array, so it reduces down to one dimension. And then over here you can say give me back all the rows with empty slicing comma 2, and this will give us back the column. Okay, so the column, oops, I have to define these things. Okay, so that's slicing, and so we got more time here. So let me, we can do calculations, just like you can do calculations with arrays in, or vectors and matrices in R. We can do calculations with vectors and matrices in Python. Oh, here we go. More stuff. Okay, let me. We'll do concatenating arrays. All right, so we can say x will be np.arange 0 to 4, 1, and y will be np.arange 100, 105. No, 104, 1. Okay, and we'll print these just so you can see. Print x, print y. Okay, and so we have 0, 1, 2, 3, and 100, 101, 102, 103. Okay, we can concatenate these things using np concatenate, and oh, and if I think I've told you, but you can hit tab, and it will kind of give you some things that you can go with. So I'm going to just say np concatenate, and I'm going to give it x and y. What am I doing here? Oh, sorry. I have to put it in a list, okay? And this will kind of stick the things together. If I want to, I think I can do np concatenate x and y, and I do axis equals, what am I doing wrong? Oh, wait, sorry. I think I do v-stack, vertical stacking. Sorry. Okay, so if you want to, so concatenate kind of just takes the two vectors and sticks them together. If you want to stack them vertically, and if they're the same length, you can do v-stack. You might have let me do x matrix is going to be np.reshape. We're going to take x and reshape it so that it's 2 by 2, and y as a matrix will reshape y, so it's also 2 by 2. And let's print those things out just so we can see. Okay, so we have those things, and you can concatenate those. Concatenate x and y. Oh, not x and y. X matrix and y matrix. Okay, and this will we'll paste them together like that. Okay. Here, let me do a print so it looks better. You can also np.concatenate xm ym axis equals 1, and then let's do axis equals 2. Yeah, wait, axis 0 and axis 1. Okay, so if you concatenate by default on the 0 axis, which is vertically, that's what you get, and if you can concatenate on the axis index 1, which concatenates them horizontally. Yeah.
How come you couldn't use the axis part before? You had to use v-stack? Does that mean?
You know, I think I was just messing up here. Okay. I think because I'm having to use my brain, which is I bet it'll work now that I see this. x, y axis equals 0. I bet this will work. Yeah. Yeah. No. Other way? Am I doing this wrong? Sure. Axis 1. No. Out of bound. Oh, yeah. No, it's because yeah, this makes sense. Okay. So, because if I do the shape, what is x dot shape? There's only one dimension. So on the first axis 0, we can concatenate that way, but there's nothing over here. So it says this doesn't. It's axis 1 is out of bounds for an array of dimension 1. Yeah. Okay. All right. So this is what we have. Concatenating. Let me think if I have to do anything else. Okay. So yes, we have VStack and we also have HStack. So you can do np VStack xm and ym. And then np.hstack. So this is what we have there. Okay, so there it's effectively the same thing as concatenate along axis 0 or axis 1, but you can do vstack and hstack. You know, whatever is easier to remember. Okay, we can do math operators with Numpy arrays. Okay, so I've got, again, we'll print x, we'll print y, just so we can see these things. Print our x matrix and print our y matrix. Okay. So you can do something like x plus 5, and it'll add 5 to each of these things. You can do x plus y, and it will add them accordingly. Similarly, xm, oops, what did I do? Oh. Okay. Xm plus 5 and xm plus ym. You can do just basic array and vector and matrix operation kind of element wise there. Other things, let me just reference our textbook for well, so basically other math functions work as well. We have you can do products. Okay, so you can do the dot product. What is this? np dot of x and y. Okay, so this is so we got 0, 1, 2, 3, and 100, 101, 102, 103. This is the equivalent of 0 times 100 plus 1 times 101 plus 2 times 102 plus 3 times 103. That's the dot product. You're kind of the inner product there. np dot for x and well, I guess okay, this is basically a matrix multiplication here. if I print xm, print ym. You have x times y. This is going to be element-wise multiplication, and also element-wise multiplication there. I think our linear algebra functions, what else do we need? Okay, I think I've got to, we'll save more of this, these NumPy operators for Friday's lecture, but I guess I'll fill out this section a little bit more on math operators, basic math operators, and then there's some cool things that you can do with NumPy arrays, which we'll go over on Friday.